Lesson 2.4, Real Zeros of Polynomial Functions. Most of the things we discuss in this lesson are going to be a review of things we discussed in Algebra 2, but before we move forward, it's good to resurface some of these main ideas. First thing we are going to review is the remainder theorem. If a polynomial f of x is divided by a factor of x minus k, then the remainder is r equals f of k. So whatever this factor is we're dividing by that k value, if we would plug that same value into the original function in for x and simplify, the value we get for the function is going to be equal to the remainder we get if we use either long division or synthetic division. So in this example we have f of x is equal to 2x squared minus x plus 12, and we're dividing that by a factor of x plus 3. First thing we should do is rewrite the factor we're dividing by. If that's x plus 3, you can think of that as x minus a negative 3. Because when we're dividing, it's always x minus whatever our k value is. So in this case, our k value is a negative 3. First thing I'm going to do is find the value of f of k, in this case f of negative 3. Which means everywhere I have an x, going to substitute negative 3 in for that. So we have 2 times negative 3 squared minus a negative 3 plus 12. If you go through and simplify that, negative 3 squared, 9. 9 times 2 is 18. 18 plus 3 is 21. 21 plus 12 is 33. So f of negative 3 is equal to 33. Now we're going to go through and divide these two polynomials. So we have 2x squared minus x plus 12 dividing by x plus 3. If we're dividing by a linear binomial, linear meaning the exponent value on our variable is 1, and a binomial meaning two terms, that's what we have, so we can use synthetic division. So we call synthetic division, we create our box. The coefficients we put across the top here come from the original polynomial, so we have 2, negative 1, and 12. The value we put outside our multiplier is going to be that k value, which in this case is negative 3. So synthetic division, bring down the 2, multiply diagonally, get negative 6, add vertically, you get negative 7, multiply, get 21, add vertically, you get 33. So this is what the remainder theorem is telling us. The value we get when we divide these two polynomials, the remainder 33, is going to be the same value we get if we plug that k value into our original function. Notice here, remainder of 33. Notice here our function value, 33. They're the same. That is what the remainder theorem tells us. In this next example, we're going to review long division to find the quotient and the remainder. So we have 2x to the fourth plus x cubed minus 3, and we're dividing that by x squared plus x plus 1. When we're using long division or synthetic division, if we're missing a term in our polynomial, we need to make sure to account for that missing term. In this case, we're missing an x squared and an x. So when we have those place values, we need to make sure to put a 0x squared and a 0x in for those missing place values. Okay? So long division, first thing we're going to do, we have our dividend, the value we put underneath our division sign, and our divisor. We need to look at the first term in our divisor, which is x squared. What do we have to multiply by x squared to get 2x to the fourth? Okay, so we're going from a 1 to a 2, so we know we have to multiply by 2. We're going from an x squared to an x to the fourth, so we have to multiply by an x squared. So we need to multiply by 2x squared. If we take x squared times 2x squared, we get 2x to the fourth. I write my x squared term over here so that it lines up vertically with the x squared term I started with. Now we got to take this 2x squared and multiply it by all three terms in our divisor. So 2x squared times x squared, 2x to the fourth. 2x squared times x is 2x cubed. And then 2x squared times 1 is 2x squared. And we're subtracting all of those values. So all of these become negative. Now add vertically, 2x to the fourth minus 2x to the fourth is 0. We have an x cubed minus 2x cubed, which is negative x cubed. And then 0x squared minus 2x squared minus 2x squared. And then bring down everything that follows. Now we're going to repeat that same process. We're looking at the first term in our divisor, x squared. What do we have to multiply by x squared to get negative x cubed? Well, we have to multiply by a negative x. Again, lining that up vertically with our original x term. So negative x times negative x squared is minus x cubed. Negative x times negative x is minus x squared. And negative x times 1 minus x. We're subtracting all of these values, so the signs are going to change to the opposite when we combine these two. So negative x cubed and x cubed, these cancel out. Negative 2x squared and a positive x squared, we get negative x squared. And 0x plus x, we get plus x minus 3. Again, we have to repeat that same process. What do we have to multiply by this first term in our divisor to get a negative x squared? Well, we have to multiply by a negative 1, so we put that across the top. Negative 1 times x squared, negative x squared. Negative 1 times x, minus x. Negative 1 times 1, negative 1. We're subtracting all these values, so we change the signs to the opposite. Now if we look, negative x squared plus x squared cancels out. We have an x plus x, so we get 2x, then negative 3, and positive 1 minus 2. Here we would try to repeat the same process. What do we have to multiply by x squared to get 2x? Since the degree of our term in our divisor is greater than what we have left, this expression, what remains, becomes the remainder. Okay, so we have 2x minus 2. At the top, we're going to add our remainder, which was 2x minus 2, and put that over our divisor, which was x squared plus x plus 1. So our 2x squared minus x minus 1, that is our quotient, our q of x function. And the value we have left, this is the remainder, which you'll see as the r of x function. Okay, so just a review of using long division. Next, we need to discuss a few more theorems. The first one being the rational zeros theorem, also called the rational root theorem. So suppose f is a polynomial function with a degree n greater than or equal to 1 with integer coefficients. P is going to represent the factors of our constant term, and Q is going to represent the factors of the leading coefficient. If we have a polynomial that meets these conditions, then this theorem allows us to find all of the possible rational zeros. Okay, this doesn't tell us which ones are going to be zeros or solutions. It tells us our list of possibilities for the rational zeros. So what we need to do is take P, which are the factors of the constant term, and divide those by Q, the factors of the leading coefficient. That creates our list of possibilities. Now we're going to go through an example applying the rational root theorem. So we want to find all the real zeros of f of x equals 2x to the fourth minus 7x cubed minus 8x squared plus 14x plus 8. If we apply the rational root theorem, we're looking at our factors of our constant, which is 8. So we're listing all those factors, plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. We need a positive and a negative for each one, because to get a positive 8, I could take negative 1 times negative 8. So that's why we have to account for the positive and negative for each factor. And then we're dividing that by the factors of our leading coefficient, which is plus or minus 1 and plus or minus 2. To make our whole list, we have to take each number in the numerator divided by every number in the denominators. We're taking all these terms divided by 1, which is just going to be itself. So plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And then we have to take all these terms in the numerator divided by 2. So we have plus or minus 1/2. 2 divided by 2 is 1, which we already have. 4 divided by 2 is 2, which we already have. And 8 divided by 2 is 4, which we already have. If you already have one of those factors, you do not have to rewrite it. So using the rational root theorem, these numbers represent the possible rational zeros for this polynomial. That does not mean those are going to be ones. It's just if there is a rational zero in this polynomial, it has to come from this list. If you look to the right, we have a graph for this polynomial. So we're looking for where this graph crosses the x-axis. If we look, we have 4 different points where it crosses. We're trying to determine if any of these points, any of these x-intercepts come from our list. If we look, we're crossing at an x value of 1, 2, 3, 4. 4 is one of our options, so we're going to use synthetic division to verify whether or not 4 is actually a 0 to this polynomial. So using synthetic division, list our coefficients. We have 2, -7, -8, 14, and 8. Bring down our 2, multiply diagonally, add vertically, multiply diagonally, add vertically, and then finally we get -8. So we have a remainder of 0. Using synthetic division, if we get a remainder of 0, that implies that 4 is a polynomial, or a 0 to this polynomial. If we know that 4 is a 0, then that implies x minus 4 must be a factor. So what we can do is take our original polynomial we started with. If we know 4 is a 0, x minus 4 is a factor, the numbers down below using synthetic division represent the polynomial that remains. So if we started with 2x to the 4th and divided by x minus 4, this is going to be an x cubed. So we have 2x cubed plus x squared minus 4x minus 2. So far we factored this polynomial down into this. Going back and looking at our graph, we want to determine if there's another value we can check. It looks like -1/2 is another possible rational zero. That's an option from our list. So we're going to check -1/2 using synthetic division. So if I would go through and check -1/2 to see if that is a 0, notice when I use synthetic division, I'm not using the coefficients we started with in the original polynomial. I'm using the coefficients that remained after we did synthetic division the first time. So we take 2, 1, -4, -2, bring that down here. If we go through synthetic division, we get a 0 as our remainder, which implies that -1/2 is a 0 to this polynomial. So now if we write this in factored form again, we have f of x equals x minus 4 because 4 was a 0. X plus 1/2 is a factor because -1/2 was a 0. And then we write the polynomial that remains. If this was an 2x cubed, this is going to be a degree 1 less than, so this is 2x squared plus 0x minus 4, which we can just write as 2x squared minus 4. The next step is to try to break down 2x squared minus 4. Looking at those two terms, they have a factor of 2 in common, so we can factor that out in front, and then we'd have an x squared minus 2 left. So the last step to breaking this down, we have 2 times x minus 4 times x plus 1/2. And now looking at this, x squared minus 2, even though 2 is not a perfect square, we can apply the difference of squares pattern. So if this is x squared, we know this is going to be x and x. One's going to be positive, one negative. And then we look at what is the square root of 2? Well, it's just going to be radical 2. So we can break that up into x plus radical 2 and x minus radical 2. So this is our original polynomial in factored form. We use synthetic division and the rational root theorem and the graph to help us break it down into this form. If we would set each of these factors equal to 0 because of the zero product property, we would get x equals 4, -1/2, and then we'd have radical 2 and negative radical 2. So we have 4 zeros to this polynomial. If we looked at the graph, we had 1, 2, 3, 4 x-intercepts. Here would be our positive 4. Here's our negative 1/2, negative radical 2, and positive radical 2. We also have the factor theorem, which says a polynomial function f of x has a factor of x minus k if and only if f of k is equal to 0. Okay, so this comes from our remainder theorem we talked about earlier. Now we're just specifically applying it to if we get a remainder of 0. If our remainder is 0, then that implies that x minus k must be a factor. Now down below we have some fundamental ideas. For a polynomial function f and a real number k, the following statements are going to be equivalent. First, we have x equals k as a solution or root of the equation f of x equals 0. Second statement, k is a 0 of the function f. The third statement, k is an x-intercept of the graph of y equals f of x. And the fourth one, x minus k is a factor of f of x. We've discussed these ideas in the past. We've reviewed and talked about when we're referring to the solution, the root, the 0, and the x-intercept. That's all referring to the same idea. Okay, it's the same concept. It's just different whether we're talking about solving an equation or looking at the graph of the equation. The fourth statement is new, but it comes from our factor theorem up above. If we know k is a 0, then x minus k is going to be a factor. The last thing we're going to discuss in this lesson is the upper and lower bound test. You don't necessarily have to write this down. We're just going to go through this so you're aware of the process. So suppose f is a polynomial function of degree n greater than or equal to 1 with a positive leading coefficient, and then suppose f of x is divided by x minus k using synthetic division. If we do this, if k is greater than or equal to 0, and every number in the last line is non-negative, so it's positive or 0, then k is an upper bound for the real zeros of f. If k is less than or equal to 0, and the numbers in the last line are alternately non-negative and non-positive, then k is a lower bound for the real zeros of f. So we're going to go through, start with a polynomial, divide it using synthetic division, using two endpoints, a lower bound, upper bound, and then use synthetic division and these ideas to verify that it is a lower bound or an upper bound. So in this last example, we want to show that all the real zeros of the function lie within the given range. We have f of x equals 2x to the fourth minus 7x cubed minus 8x squared plus 14x plus 8. And we have the given range of negative 2 to 5 with these endpoints included. So first we're going to check whether negative 2 is a lower bound. So we take our coefficients from our polynomial, 2, negative 7, negative 8, 14, and 8. And we're going to use synthetic division and look at what happens to the signs on all of our terms that end up in the bottom. So check with negative 2, bring the 2 down, multiply diagonally, add vertically, and multiply the last step to get 28 and 36. So using the test, if our k value was less than or equal to 0, which negative 2 is, if this is a lower bound, then the signs are going to alternate between being non-negative and non-positive. So positive, negative, positive, negative, positive, they alternate between non-negative and non-positive. So this verifies that negative 2 is going to be a lower bound for the real zeros of this function. Using a similar idea, we're going to check whether 5 is an upper bound. So we take our coefficients, 2, negative 7, negative 8, 14, and 8. Again, using synthetic division and looking at the signs on our terms that end up in the bottom, checking with 5, bring down our 2, multiply diagonally, add vertically, five times 49 is going to be 245, and then add vertically, 253. So using the test, if we're trying to determine whether a value is an upper bound, first that value has to be greater than or equal to 0, which 5 is. We look at all of the terms in our last line. If all of those terms are non-negative, then that verifies that 5 is an upper bound for the real zeros of this polynomial. Just a quick review of this lesson. We talked about many ideas from Algebra 2, the remainder theorem, the rational zeros theorem, the factor theorem, and then we used some of those ideas to find the real zeros of polynomial functions. We also reviewed synthetic division and polynomial long division. The new idea for this lesson was the upper bound and lower bound test. Okay, so make sure you review that process. We'll go through another one of those examples together in class.